Okay, here we are going to learn about determination of order of chemical reaction. So already we learned determination of order by half-life period, half-life method, and graphical method. Today I'm going to talk about rate equation method. We are going to actually use the integrated form of rate equation to find out order of given chemical reaction. Let me say a reaction of this type A is converted into product. Here my intention is to find out order of this chemical reactions. What can I do for this? I know a time this is time time at zero time. The initial concentration taken is A mole per liter and the product is not formed, so it is 0. At time t, some x mole per liter of product is formed. The remaining unreacted molecule will be A minus x mole per liter. So this is known to us very well. So I'm just going to find out the unreacted molecule, the amount of unreacted molecule present in the reaction mixture at various time t. So I'll start a reaction, then at every 5 minute, that is 5th minute, 10th minute, 5th minute, 10th minute, and 15th minute, and 20th minute, and etc. At various time interval, I'm going to various time interval t, I'm going to find out the unreacted molecule and the concentration of unreacted molecule present in the reaction vessel. That is, I'm going to find out A minus x value. If I find this value at various time, I simply use the integrated rate equation, the integrated form of rate equation. For the first order, I know for the first order, the equation k equal to 2.303 by t logarithm a by a minus x. So here I have I will find out k value. I will find out k value at various time interval. Say I'll substitute here, for example, for instance, I will substitute here 5 and logarithm A is my initial concentration is known, and A minus x is a concentration of unreacted molecule at time 5th minute or at time t. So the same way I'm going to find out the k value at the 10th minute and the k value at 15 minutes. So I know I experimentally found the A minus x value, that is unreacted molecule, at various time, that is 10th minute, 15 minute, 20th minute, and 25th minute, etc. So all these times I'm going to substitute the time and the A minus x value. The A is initial concentration is known. If I get constant value of k, if I get constant value of k, then I'll conclude that this reaction belongs to first order reaction, because I used first order integrated form of rate equation. I substituted the experimentally found the unreacted molecule A minus x at various time t. If I substitute this value in this equation, if I get a constant k value, then I conclude that this reaction is first order reaction. Then if I don't get a constant value, then the reaction is not first order reaction, right? So if the reaction is not first order reaction, then I have to find out, I have to check it with the other rate constant, integrated form of rate constant equation. Let me write for a second order reaction. It is k equal to 1 by t 1 minus A minus x minus 1 by A. So this is the equation for second order reaction, rate constant equation for, or integrated integrated rate equation for a second order reaction. If I substitute a minus x value, because I already found a minus x value for the given reaction, for this reaction, and the initial concentration and time. If I substitute all the experimentally found value in this equation for various time, if I get again constant k value, then I'll conclude the reaction is second order reaction. If I don't get a constant k value, the reaction is not second order reaction. So then I have to check for a third order reaction. K equal to 1 by 2t 1 by a minus x square minus 1 by a square is an integrated form of rate equation for the third order reaction. If the reaction is not first order, if the reaction is not second order, then I will have to check for the third order. Then the same experimental value is substituted in this equation, that is time, and a minus x and a value is substituted for various time interval. If I get constant value, if k is constant for various time, then I'll conclude the reaction is third order. If not, then I'll have to check out for a zero order reaction. I know zero order reaction, k equal to x by t. So here you found the value of a minus x. So if you subtract a minus x, that initial concentration, and at various time the unreacted molecule, if you subtract a minus x from a, then you will get x value, right? So here you substitute at time t x value. Here you have to substitute at various time the x value. If you substitute, if you get a constant k value, then the reaction is zero order reaction, right? If you get a constant k value, then the reaction is zero order reaction. So this is how you can find out equation rate. You can find out order of a chemical reaction by using rate equation method. Actually, we use not rate equation. Actually, we use integrated form of rate equation. This is integrated form of rate equation. Then next, I would like to explain about Ostwald method. Ostwald method this is actually introduced by Ostwald in 1902. In 1902, this method was introduced, and again this method is also a very simple method. This method is also very easy to understand. Here let me take the same type of a reaction. A reactant A is converted into product. Here I'll write the rate expression, rate equal to minus dA, change in concentration of a reactant with time, is equal to K times this method is used to find out the chemical reactions of this type. See, A, B, C is reacting to give product. Here I will write the expression, rate expression, rate equation for this reaction. In terms of A, I am writing the rate expression. Is this K power? I don't know what is the power. That's what this is what I'm going to find out. This is order, and B power, B and C power C. The order, the total order of the reaction. See, um, see, A is reacting with B, reacting A, B, C reacting to each other, and give product. Here the order is actually equal to the sum of powers A plus sum of powers of concentration terms in a rate equation. So therefore order equal to A plus B plus C. This is order. I'll write again the rate equation, minus dA by dt K A power A, B power B and C power C. If I the rate actually depends on A, B, C. If I take any two of the reactant in a large excess amount, in a large amount, then we learn that the rate will not be dependent on B and C. For instance, I'm going to take large quantity of B and large quantity of C. Therefore, this reaction rate of this reaction will not depend on B and C. Then comparatively, A is smaller amount I'm going to take. See, I'll repeat again. Here I'm going to take smaller amount of A, and comparatively very large amount of B and C is taken to carry out this chemical reaction. Then I learned that if you take large quantity of reactant, then the rate will not depend on those reactant molecule. So the rate of this reaction will not depend on concentration of B and concentration of C if I take them in large quantity. So the rate will depend only on A. So therefore this rate equation will become, because it is not, the rate is not depends on K dash, the rate is not depend on B and C. So this two term which I'm going to remove from this equation, so I will get, it depends only on, the rate of this reactions now only depend on concentration of A. Okay, now I'm going to use any one of the other methods, like half-life method, or it may be rate equation method, or it may be graphical method. I use any one of the method to find out the order A with respect to A. Right, now I will know the value of A, that is the order with respect to A. Next, what I'm going to do is I'll take A and B in large quantity and B small quantity. Then if I carry out the reaction, then the rate will depend only on B. Then I use any other method to find out the value of B. In the same way, order with respect to C is found. So now the total order can be found, will be equal to A plus B plus C of the reaction. Right? So if you take except one of the reactant, all other reactant are taken in large quantity. Therefore the reactant, the rate of the reaction will not depend on the reactant which is taken larger amount. So that will depend only on the reactant which is taken smaller amount. Rate will depend on only the reactant which is taken smaller amount. So this will not be the rate equation. Then the rate equation becomes like this, that rate depends only on one of the reactant which is taken smaller amount. So you use any of the method, like half-life method or graphical method. Use any one of the method to find out the A value. Then the other two molecules taken in large amount. Then the one molecule is taken smaller amount, the other two molecule is taken larger amount. Then the here with respect to B, A and C is taken larger amount, B is taken smaller amount. Then the B value can be found using any one of the known method. So if you add all the values, then you will get order of this reaction. So this is called Ostwald method of isolation method, right?